Hello, hi YouTube, everyone on the call. We are recording this. Today I'm presenting. My name is Vahan in here with Matt. I think everyone is familiar here. I'm going to present a quantum machine learning paper. This one is from 2017 from Nature. So it's going to be an introduction to quantum ML. I don't have background in quantum computing, but I try to prepare for this presentation. So please interrupt, ask questions, bring in your quantum knowledge, so we can have a productive discussion here. Okay, so let's go to the paper. So this is a review paper about the state of art in quantum machine learning as of 2017. There are a couple of new research review papers on the topic, but we start from this as an introduction, because we have never done quantum ML here before. And then if anyone is interested to talk more about quantum ML, we can do another session next week. There is another review paper from last year, so that can be more up to date. So here we'll assume we are talking about state of art on 2017. Right, so as I said, it's a review paper, and they start with talking about ML, about finding patterns. So I guess that part is not very interesting for this audience because we speak about ML every week. But what's more interesting is how does quantum computing relate to machine learning? Right? What sort of problems are studied and why? And what are the challenges? There are a lot of problems here actually, because even though in theory things can be sped up by a lot, in practice it's not always true. We'll see that later in the paper also. Right. So the introduction is about ML, about classical ML, things like linear regression, support vector machines, but also a bit of deep learning. Again, this is 2017, so not transformers yet. Yeah. Right. So let's actually go down to, let's talk about quantum speedups, right? Because the whole point with quantum computing is quantum speedup, the main point. Right? We want to be able to speed up algorithms, especially the NP-hard problems, to be solved in shorter times or become solvable in general using quantum computers. If you have a comment, just write in the chat or unmute and speak if you have on the call. Yeah. Okay. So quantum speedup. So there's a nice table here covering the speedup. So speedup means the rate of improvement, right? So square root n means it's a quadratic improvement. If you use a quantum computer, log means it's an exponential improvement if you use a quantum computer for the same problem. Okay. So those are number of algorithms. So we talk about quantum PCA, quantum Boltzmann machines also later. We speak about the least squares, but in terms of deep learning, it also actually in a surprising way, deep learning may be the most straightforward application according to the paper, but we'll get to it. So this is a nice table of summarizing of performances. Okay. Any comments here?
You say that an improvement of log n would be an exponential improvement?
It's like a notation thing. Yeah, so not improvement of log n, so it's a speed up, right?
Shouldn't that be like the speed of these log n means that like you're moving from n log n to n in terms of complexity?
So you go, so for example, n log n.
Yeah, like n log n. Like
The log part, but
So you go from n to log n, right? Or you go from n log n to log n.
no, that's what I was understanding was that if you have a speed of log n, that means that you can go from n log n to linear.
No. So it's about notation. So this here
That's what I
means,
yeah,
yeah.
understood.
That's why I clarified, right? Log n means exponential improvement because it means you go from n to log n, or actually you go from,
I got this to the logarithm of
yeah, exactly. So you get exponential improvement. So you go from
Okay, so
log n to log n, or you go from n to log n, right?
yeah, it's of course much slower. And typically, if you have n again, you sometimes just ignore the log n part, even though of course can be important.
Yeah.
But it's so much more dominated by the n, especially for large numbers. So it's,
yeah, maybe.
Or if you go from n squared to n, this would be the square root n speed up. Okay?
Square root speed up would be from n
Yeah.
squared.
So whatever the complexity, you apply this function there. That's the speed up.
Okay. Ah,
Okay, so you don't divide, you apply the
okay,
function,
got it.
right?
Yes, yes, yes.
Um,
So it's log of the original complexity.
yeah,
Wow, that's not what it
Okay.
looks like, but okay.
yeah, that's why I wanted to clarify here because it took some time to
Okay.
consider the difference. Okay. There are a few terms I want to talk this HHL. We speak about this. It's an algorithm. QRAM is a system to access to represent a non-quantum data as quantum data. Because if you observe, if you have an image, you want to do ML on that, you need to convert it into quantum data. Right? So QRAM is a quantum random access memory. So it's a way to represent that. We speak about a few algorithms, but the main thing is here quantum speedups. And also there is another thing we should cover actually. Let me scroll down. Actually, no. Okay, thank you. Um, okay. Any more questions about the speed up, or should we talk about linear algebra, quantum linear algebra? Okay. So basically, quantum linear algebra is made possible by an algorithm called Q-BLAS. You know, BLAS, it's a linear algebra. It's called uh, it's a linear algebra library that makes all of linear algebra very efficient. It's called linear algebra subroutine. Okay.
yeah, plus, yeah.
Yeah, it says BLAS. Yeah. Basically like some problem stuff. So everything we do now, or with blast really, so there is a quantum version of that makes linear algebra on quantum data possible. So maybe I did actually mention this quantum data. So these are represented as qubits, like as qubits. So qubit is a the quantum version of bits, right? Instead of 0 ones, we have a quantum state. That's a linear representation between the two superpositions. Unless you think that. Okay. So you would have a linear combination between, let's say, 0 and 1, but it would be complex numbers describing the superposition. Superposition means photon or any other quantum object can have two positions, or more than infinitely many positions, right? Yeah, and we don't know which one it is, so we have to represent it as a superposition. Okay. There are a few other quantum terminology here. I try to clarify, or if anyone knows quantum physics, please help clarify these steps. Okay. Right. So QBLAS is an algorithm that runs linear algebra. So solves linear equations, inverse matrices, hence you can solve the D-squared problem. Once you have your data in a quantum state. right? That's the big assumption. The other assumption is after you solve the linear algebra problem using a quantum computer, you have to represent your solutions back into classical data. So those two are big bottlenecks. We'll talk about them later. Okay, so that's glass using linear algebra. And then again, because of this qubit representation, we are able to reduce the time complexity. Those are time complexities, exponentially or quadratically, depending on the actual problem. So for PCA, it's exponential reduction. Okay. They don't go into the details how exactly it works because it's an ML paper, not a linear algebra paper. And yeah,
I think one of the issues could be, I'm not quite sure whether that's still the case, that these quantum operations, they would not give you the right answer all the time. Typically, you would have to run several times in order to get. And also because every time you do it, it gives you slightly different numbers.
yes, they think about that later. Yeah, go ahead.
But that's why people don't know yet whether they're actually faster, or they can get a classical algorithm.
Yes. Yeah, they mentioned it at the end in the conclusion, saying that it's all great, but to have it's very hard to get empirical evidence that this is always better than classical algorithms, especially because there is no theoretical lower bound for quantum algorithms. So if we have a theoretical lower bound, we know it's always faster than a second bound. Yeah. We don't have to. At least in 2017, we didn't have it. Things may have changed now. Okay. Okay. About PCA. So again, you know what's PCA. You take the eigenvalues and the eigenvectors of the for data matrix. We take only the largest. If there is a significant drop in eigenvalues, we take only the large part, cut everything 0 or close to 0, and then reconstruct the matrix, which now has much lower dimensions, right? Because we cut the eigenvectors. So similar thing, except now we do this with quantum states. So here, I should pay attention to this little notation here. This is how we code qubits, right? So this is a qubit now. With a vertical line on this area here. Okay, and then we to apply the same PCA algorithm with a quantum representation, with a quantum algorithm, we need to bring the observed vectors into a quantum state, and we use this Q graph for that. There's a quantum memory, okay, which maps the vector into a quantum state. Right, so V is the observed vector, and this cubic B, there's the notation here.
What is a quantum state?
Good question. We talk about positions, right? So you would have, instead of having 0 or 1, you can have 0 or 1 or anything in between. Except now 0 or 1 are also complex numbers. Yeah. Okay, so that's like quantum state.
It can get slightly more complicated because usually you're not only interested in the 0 and 1, but
yeah.
The real interesting stuff involved.
Yes, please.
I don't know whether.
So are we our in-house physicists? So how can
normally, right, we would say we can have a system that is either 1 or 0, right? So if you want to represent it as classical vectors, you would say this would be our 1, this would be our 0, and it's either one of those, right? The quantum physics, what we can say, we can add them together some base that would be the most generic version of a single qubit, right? So it's somewhere in between plus and 1, 1 minus 1. Probably don't even know it. I think we even have an amplitude as well. Sorry.
Mm-hmm. But that's if you represent it as a complex number.
Well, would this be a qubit? Yes, but no, right? Because you can't ever find the overall phase of a state, right? So
You need, so you need to.
you need the two states, and only then the phase in between becomes
Mhm.
meaningful, because you can always ask, what is a measurement? A measurement can essentially tell you only one of the two.
Mhm.
And say if that's why we need actually the amplitude. If I want to measure something, special case. If I want to measure something, say we have the state alpha 1 minus alpha. If I want to measure, and I have an apparatus that can only measure 0 or 1.
Does it have a name that you can only measure 0 or 1?
Say again?
Is there a name that you can measure only?
It's that is the definition of a measurement. A measurement is any system that it sort of spans orthogonal basis. Here, in 0 and 1, 0, 1, and 1 and 0, they are on orthogonal basis of the eigenspace, right? However, any combination of those that is again orthogonal also would be a measurement.
Mhm.
So that is one example would be light. So say one typical example is light. Light can be polarized, could be x direction polarized, y direction polarized. So you could say if I measure a photon and it's x polarized, it's a 0. If it's y polarized, it's a 1.
Mhm.
However, what happens if I have a diagonal? I can measure my light diagonal.
Then you
Then,
need both.
second,
Then you need both.
and that measurement would be in fact a superposition of the two.
Which you would find by sampling, like taking multiple measurements and taking the
Well,
average.
that's where it gets interesting. So say I want to measure this data, this a little bit of 0 and a little bit of 1, which I just do by taking my polarizer, and I have let's keep it a bit simpler. Let's just say I want to measure 0. I want to measure 0, and I have such a state. What actually is going to happen? I would see alpha square of the time. I would get a measurement. Yes, I hit it, and 1 minus alpha squared times I would get no result. So the detector wouldn't detect it. So these are probabilities. Right? So I have, even though I have a state that is perfectly defined, there's like that's like the lowest description of nature. There's no uncertainty about the state. The moment I measure it, I actually have a chance of different results. And that is usually what happens in all of these quantum systems. But you don't have one state, but you have several states together. So beta 0, 1 minus beta 1, which could be two different photons.
Mhm.
This is a simple state because they are a product, right? I can measure one, and whatever the other is doesn't depend on what I measured on the first one.
Mhm.
Really, really tricky becomes when this is actually sort of product tensors, right? When we have a state like this, plus 0, 0. And let's say we have some factors in there as well, right? So they always have to be normalized. The amplitude has to be normalized to 1 because it can be either one or the other.
So it's basically like if they're collinear.
It's yes. So in this case, they would be perfectly correlated, right? I can measure the first one, and I would exactly know what the other one is, because no matter what the first one is, the other one must be the same because that's how I prepared them. However, if I measure the first one using any of these, I still get only like a 50% chance in each direction. So now it becomes really, really, really strange. Imagine these two could be in principle very, very far apart, right? So I have photon A, photon B. They come from the same source, from the ends of the universe. And I know that the whole is in such a state. I can measure on one side of the universe 1. I would know that the other side of the universe is also 1. And then a guy who is there and measures this, and afterwards you come back to the middle of the universe and compare, you would indeed see that they all the same. But it's not really causality either, because even though I discover forces, I can't send information that way.
Yeah.
And
Wait, sorry, it's a notation that you had.
yes. So this is a tensor product. So you could
It's two quantum bits that are both one.
yeah. So it could be something like this. sorry, it's like a vector tensor product.
Oh, yes.
And they work in different they are different systems, right? So this could be a photon, this could be an electron sound device. It doesn't have to be the same system. The physics, of course, is the same. What typically is the difficult thing is in order to make any meaningful quantum, it's always easy to have systems that are product, right? Because it's very easy to just have one here that don't interact. However, in order to get something like this that has these quantum properties that they are not independent, which you always need for these quantum algorithms in order to get anything out of it, you have to somehow let 1 and 0 interact so that they get entangled. That's when in practice it becomes difficult. Because on the one hand, you want your qubit stable, meaning that you have a state, take an electron and you push it spin up. Typically, after a couple of seconds, you can look again and it's some sort of random because there's temperature. Whereas a photon, it would be very, very stable. But electrons, for example, are very good at interacting. So it's very good to actually create states that are sort of entangled. Lights, it's very difficult. But light famously doesn't interact very well unless you do some very small things to it. And so it's very difficult to create these days. So there's always a trade-off in practice between having systems that are stable that can actually do meaningful stuff for like, I don't know, tens of seconds, a long time, these kind of things, versus systems that you can actually manipulate into something that makes meaningful states in order to undo any of these algorithms. And then having it provably so meaning that you have, I think right now, I think that the maximum they have is like 40 qubits. So essentially, you have a 0 and a 0 and a 0. So that like 40 times. So that would be like a maximum system you can I think right now build where you have.
I think there was a 50 qubit, 53 qubit Google.
Yeah,
but it's never more than 100, right? Like 50,
but for the time being, and so right now there's a bit of a race on what system actually is reasonably stable that I can do the stuff, but at the same time I can actually combine them. And there is no good answer.
Yeah.
Sorry, that was.
So a lot of quantum computing now is about like finding a way to make stable qubits.
I think so. Yes. So there's usually like last year's Nobel Prize was quite in that direction, but where they actually prove these weird properties that which they can use for example for state teleportation. They can say that you by exploiting the property, you can sort of move the state from one end of the universe to the other instantaneously. But again, you have to communicate by digit, otherwise the other person can't possibly recover the state.
We covered a lot of the challenges they discussed later, which is good. Oh, it's good. Thanks for that.
I think for this paper repetition is useful.
Yeah, I think there's lots of terminology. I found the entanglement quite amusing, like how electrons or any other objects can get entangled even though they are light years away from each other.
Yes,
It's quite.
it's the thing is. I remember I had a friend who always like quantum mechanics. Everything is connected. to Everything. It's damn hard to get these entanglements even across a table, let alone half the universe. So, well, it's easy to say we are all entangled.
But we don't know how to control them, right? But
Yes, and then like more distance, they sort of decay. Like anytime you have any random, like natural randomness, like some gas in the air, it gets lost very, very, very quickly. So that's why these they work in like very specific setups, like vacuums or so, where they have very little noise of the environment, or using systems like optics that don't necessarily interact much with everything around them, so you can get stable behavior.
cool.
I have one question. So, which is, how does entanglement help with the computation?
Very good question. That very much depends on the algorithm. I don't know whether you go.
So there is one diagram here about. It's called. Okay, let's talk about that. So there is this quantum annealing algorithm which is used to minimize functions, right? So this is used for to learn models, right? Quantum annealing it's kind of similar in principle to simulated annealing, except that here you can have this so tunneling, right? So you can have the quantum state tunnel through these dense energy parts, right? So this is an energy curve, and you can have a quantum state here, and then it can tunnel through that.
A little bit like overshooting on the sense.
No, it's actually better because it's a way to magically find global minimum, right? It's like
As long as the walls are thin enough.
Yes.
well, even if they are not, that's the point with quantum tunneling. Even if the walls are not thin, you can just do it.
Even if it's like the peak of the wall is so high that it's impossible.
Yeah.
There's still a finite chance that it might happen.
That's the idea behind this quantum annealing thing. So you simulate the states, quantum states, but then you do it in a way that because of quantum tunneling, you end up with a global minimum, I think. Right? Even though there is a high jump here that your variant descent will never be able to overcome. So because of quantum annealing can do it. What was the original question?
I was asking how does entanglement help with
Right, but with entanglement, you have the states, two quantum states connected to each other.
Yes.
Right. So which means when when you change one, the other one is also affected. If you can control that. Am I saying
So if you measure one, then the other one automatically takes on some correlated value.
So again, I think what again it very much depends on the algorithm, but I think one of the prime algorithms is Shor's algorithm. Right? So it's the algorithm that essentially allows you to factorize large large numbers into the prime components. Which is quite useful in cryptography, like as an elite modern RSA language. Now the rough idea, and I'm not giving it a full justice, but it's again this property that essentially you can have an entangled state that that sort of, again, I'm making this up, it's probably very inaccurate. Essentially, what can do is you could have, say, your system that is something very boring like this. You have your, so that would be a state of 5 qubits. They all start on the same, they spin down situation. What you can then do is you can rotate each of them into something that is some superposition. Something very similar. Again, still a boring thing, but if you decompose it, you essentially get all the different. So you get still your original 000 state in there, but somewhere along the side you have a state that is 0, 1, 0, 0, blah blah blah. Somewhere and then all permutations. So you can essentially in a single flip of all of them together, you get a superposition that contains all possible combinations of these different states. So you have, yeah, any spin up somewhere has also spin down in the same like. And then usually what happens, you have some smart operation that tends to amplify, let's say number 1, number 2, tends to amplify the prefactor of that combination that you're interested in. For example, the one that factorizes your prime numbers. It would be like, so this could be a 2, this could be a 3, this could be a 6, 1, 5. And then again, it depends very much on the actual algorithm, what it's doing. But you run it through these combinations of uh, quantum gates, and at the end you end up with some combination of these alphas, where typically all the alphas are still there, but some of them are just larger than the others. And you remember when you measure that, and you sort of, because all of these states are again orthogonal to each other, you can measure them, and with a somewhat higher chance than random guessing, you get the right answer. If you do that several times, sort of after like a couple of trials, you will find the one combination that is better than the other, especially for things like factorization. You can test it, right? If I measure this state 5 times, I can actually multiply the numbers and see whether it's the right answer. So how the action step comes in here that actually sort of amplifies the parts that are really interesting. I don't know for sure anymore. It's been a long time, but it's when real smart people. It is a wonderful video of Peter Shaw explaining it.
In a way that we can understand.
No, it's like, I remember that one of the comments was, this guy has seen a lot because he seems just so far out. But yeah, and then so actually finding these quantum algorithms that actually prove that out is not easy.
Yeah,
It's non-intuitive.
it's probably like a complete, yeah, exactly, very unintuitive way of thinking about the problem. Because in fact, like even this idea, like a quantum gate, that sound no type of operation doesn't sound like something that we're used to when we think of operations.
Yeah, but it's probably this most similar is like an XOR or so, like something that selectively changes the phase of one of them, right? And so that's how in classical logics you have your universal. I think it's the XOR like a universal gate that in principle you can build any computer you ever want, computer using XOR gates alone. And the similar thing you can also do with quantum. You can show that any quantum gate that is minimally non-trivial, you can build in principle any quantum computer out of it. Of course, you need all the qubits and all of that jazz to make it work.
Cool. Okay, should we continue? Initially I thought this paper was a bit too short, but actually there is so much we won't cover because we need a lot more background than usual. Okay, let's talk about reading classical data into quantum machines. Right, I mentioned earlier that this is a bottleneck, and we need this QRAM system to do that. And this can be prohibitively expensive because this can make even a PCA can be exponentially hard for PCA can become exponentially expensive because converting the non-quantum data into quantum data can be a massive bottleneck, and that is the main problem why this system may not be useful. Similarly, for converting data back, after you do your learning, you have to convert it back into a non-quantum data, which will also be prohibitively expensive. So any sort of speed up we get in the algorithmic performance, this conversion is a problem. Okay. Okay, let's talk about quantum deep learning, deep quantum learning actually. So this one seems to be the best suited ML model for quantum learning, which I found interesting because let's go here. If you look at Boston machines, right? So Hamiltonian parameters. This is again a quantum mechanics term. Basically, we are trying to estimate parameter W, and this H is the matrix, and we have the input states. Okay, so the sigma is what we use to approximate the input state, and our training basically minimizes this error. Okay. From the training parameters to the real one. Even though, so this is supposed to be an expensive, difficult thing to do, but actually, if you study the gradients, you can do the gradient calculations. They say it's easy to do. Let's assume it's easy to do. You will end up with a simpler form, which or some, which is easier to solve using actually a gradient descent. This is a gradient update step. And they claim that even with large problems, you can do, I think they said 10 epochs, which is actually very low for gradient iteration, just 10 steps to find a minimum. So this Boltzmann machines can be solved very efficiently to a global minimum, basically, using a quantum machine. And there is no efficient analog of this using classical methods. Okay? The important thing is that this H is a stochastic observation.
Sorry, what was the last one?
So this H that we were using before is the Hamiltonian, right? Is a stochastic observation. No?
Yeah, the observation, yes, but H is it's something like a rotation in the space, so anything that moves.
Yeah. But the observation is stochastic.
Typically, yeah.
Okay, so they have a visualization here, like how the learning happens. This is the true state, and then you can go from the initial random state to the true state. In this case, in 10 epochs. 8 epochs, you get very close. They are like the C1.
What are the axes here?
Data dimensions, I guess, such data.
So the green peak would then be your most likely state, which would be the true. The true.
No, true state is, what do you mean?
Maybe this is tabular data, where the output is the number between 0 and 1.
Okay.
Yeah.
Or it probably it's like a distribution over
Yeah.
2D space, and you just it's a small problem though.
Yeah, it's a very small one, but they want to show that you can get there.
I guess this is could you visualize like a 25-dimensional problem.
Yes, you can't visualize, right? It's high dimension. But it's just a visualization, yes. Okay, now, remember when we said that the converting data into quantum state and back is prohibitively expensive? Now the question is, should we just do ML on quantum data directly? Right? Instead of measuring a state, an image, and then converting it back into quantum state, can we just collect the quantum data? Right? Which will solve this problem, because there is no conversion back and forth.
So when does the conversion happen? I understood that conversion will happen only every unit. Yeah.
So twice, right? So if you want to use a quantum algorithm and your data is house prices, right? Binary numbers, binary representation of numbers, you have to convert that into a qubit to your quantum learning and then convert it back into 0 ones.
Right.
Those conversions are very expensive.
Yes.
So what they're saying is, can we just measure the quantum states, at least in theory, do the learning, and then use the optimal parameters in qubit states without converting? So everything stays in quantum. Everything is a qubit. There is never 0 1.
It's still not clear how that helps you to get the answer to your problem. Right? The end result is still a qubit.
Yeah. Well, you don't.
What you're saying is like a non-interpretable form of data.
I mean, it might be, you might have a black box where it says it has the right answer inside, but not yeah, but no.
Yeah.
Well, maybe the output.
Yeah, so that there must be at some point it must have some output.
Or maybe the answer is like one number instead of. I guess if you had to generate like images or something.
Well, why images? I mean, if you measure the position of an electron, how do you measure it?
Well, you sort of shine light on it, but then typically that would be not deterministic, right? You could do exactly the same thing and you could find place somewhere else. So
yes, you find the probability distribution.
yes, but of course you have to query it and you can't do it in a single measurement. So,
Yes. Oh, that's one of the other problems they mentioned later. But this one is about not converting from 0 ones into qubits. But I think also the other way around. If you read here, the most immediate application of quantum machine learning is to quantum data. The actual states generated by quantum systems and processes. So you actually work directly with quantum data. machine learning algorithms find patterns in class data, blah, 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 right? So you don't have to do this mapping bit. Okay, then you, which is why you directly work with quantum data. I'm not sure how you actually measure the quantum data.
Yeah,
In the first place.
prepared. Yeah, I mean that's just
Yeah, a little bit of a problem, yes. Well, they're saying if you don't have to do the conversion, then you avoid full the rainfall. Maybe you can read a bit more here. There are quantum simulators, which are quantum analog computers. They simulate quantum states. Quantum systems whose dynamics can be programmed to match the dynamics of some desired quantum system. So dynamics will be given by what's the equation? Schrodinger's equation, right? So you would use the Schrodinger's equation to model the dynamics of the quantum systems.
So you can, in principle, you can always map between the two. So you can any classical or in any quantum operation you can do in a classical computer. It just might take you longer.
Yes, exactly. But they say if you can use a quantum computer, then you don't have to do the conversion to classical computer.
Yeah.
Okay. Let's continue to see what we have else here. Right, there is this other problem that can be studied is by designing and controlling quantum systems. Right? We kind of spoke about this quite a bit because especially the controlling part, right? Controlling how the quantum states change isn't easy. But let's get some more. For example, there is this thing called Toffoli gate. There are a few other things. So Toffoli gate is called control, not control. It's like it's a
Yeah, no, you're
Oh, I
right.
don't know. I would rather use.
Looked it up and you're right.
Okay. I also looked it up. I'm trying to. I think it may be here. Anyway, yeah, here. I can maybe. Can you see my screen? No. Basically, it's a gate that if you give one state, the other state can so just define automatically. Right. So that's a way to control the quantum state. So if you can use Tofu, it's a 3-bit state. So it's like 110, the other one becomes 001. So it kind of converts automatically. And then the people have been able to use those with very high accuracy to control the quantum state, right? And almost 100%. There was other work. So this, when they talk about natural dynamics of quantum networks, they usually talk about Schrodinger's equation or some other form of that, which defines how the quantum state changes.
I think that was also a big step forward in all of this. That we use document information theory, error correcting code. Talk about the really the same thing in quantum mechanics earlier. Quantum error correcting codes, where essentially, yes, you have all transmission has not 100% fidelity, but typically you can add some extra bits and you sort of measure them, and by measuring them, you bring your system back into the original state, which is quite magical as well. But so it has this inbuilt way of adding redundancy in order to keep you on track. Also not that short, so he did a lot in that field.
He's like, what's the name? No, like nude?
In that field, almost certainly. Yeah.
Okay, wow. I was thinking, what's the name of the guy who like defined information entropy?
Shannon.
Like he's like Shannon, but for quantum information theory.
But interesting that there are other people who do exactly what Shannon is like trying to quantify how much information is in any computer system. So they would be the Shannons of quite information, but yeah.
Interesting. You also mentioned reinforcement learning being used to study and represent how dynamics change in quantum systems. They don't have many details. Maybe we can find a paper and do it next time. Integrate back then. But
I was thinking if I was going to do any, it would be like the HHL algorithm for inverting a matrix.
oh yeah,
And just like going into enough depth that I could actually explain it Yeah.
Sure.
So you want a 2 hour lecture.
It's part of the blast thing, right? Or similar to that.
It's QBLAS, I think.
Yeah. They don't give the details of those algorithms here, so they just say do this, so you can do classical machine learning. Anyway, we are back to the last piece, the 4 fundamental problems with quantum ML as of 2017. Things may have changed now. If you want to find out, come to the next week session. We'll have a more up to
Are you
date.
gonna do an up-to-date one?
Whose turn is next week?
That's mine.
Okay, so there are 4 fundamental problems. We've touched on all of them just to summarize the session. Okay. The input problem by converting from bit to qubit. It seldom provides advantages in reading data, okay? Which means whatever speed gain we get from the algorithm, we may lose here. We don't even know, in theory, we can benefit. The output problem, similar but the opposite. The costing problem. So basically, very little is known about the true number of gates required by quantum machine learning algorithms. I just read the sentence here.
Sorry, the number?
A number of gates required by quantum machine learning algorithms. Yeah.
Sorry?
It's like the number of operations required by the algorithm.
There is no
Actually know how many are required.
For example,
Very large.
Yeah.
yeah, for short algorithm for standard RSA, going I think so 20,000 qubits or so, quite a bit off the 50
Yeah.
now.
So we
They
can
do
give
some large numbers
Yeah.
compared to what we're already looking at. 50 in the
Yes.
piece.
So like, you don't know how many steps your algorithm actually has.
You can't upper bound it.
we don't have the theory developed enough to upper bound them. And the current, this is from 2017 saying that there are small scale quantum computers between 50 and 100 qubits. I think it is true. I googled, like the largest one was like 60. So it's we haven't been able to build at least commercially available large.
Actually, it's also provably so, right? So because you sort of have to prove that every part of this 40 qubits can be entangled to arbitrary degree to every other part. So it's that thing that makes it really big. Also very time consuming to actually get it out because
There was one experimental machine that didn't use qubits. There was a different system that could experimentally do scale to much larger sizes, but I didn't really think that. Anyway, and the last problem is the benchmarking problem. We also spoke about this briefly. Basically, we have to do loads of experiments to actually measure that in practice quantum algorithms are actually better, besides the theoretical complexities we mentioned. And this is also very difficult to do. Okay. So this is the state of quantum ML as of 2017. Any more comments before we finish? No? Okay. Thanks for coming. Thanks people on the call. See you next week.